Here we are going to talk about solid-liquid equilibrium. And this process is one that you would use, for example, crystallization. If you crystallize out a solid, and actually crystallization is used pretty frequently when you want to purify out a product. If it's at a high enough concentration, or you can change the temperature of your mixture and crystallize out a product, you can often do a rapid purification of that material. So it's actually a good way to purify products at the end of a process. So here we're going to talk about solubility, which is the maximum amount of the solid that you can dissolve in the liquid. The distribution coefficient, which is a way of representing how the solid partitions. And we will also talk about a hydrated salt. So here is a solubility diagram. And what this shows you is the solubility. Note that the units here are not mass fraction, but they are kilograms of salt per 100 kilograms of water. And here it shows you how some of these salts, sodium chloride, for example, the solubility does not depend much at all on temperature. So you increase the temperature and you increase the solubility ever so little. But something like KNO3, if you increase the temperature, the solubility increases dramatically. So it's important how you design your crystallization process depending on the dependence of the solubility on temperature. So for example, if you have NaCl, you're going to need to evaporate this water off in order to get any crystals, because cooling it isn't going to do you a whole lot of good. But on something like KNO3, by cooling it, you get your crystals out, in which case this water stream would not be necessary. So you have, entering the process, you have a solution of the solid in the liquid. And here we've identified a mole fraction of Z sub S, which is kilogram of solute per kilogram of solution. So even though that solubility diagram gives you solubility as kilograms of solute per 100 kilograms of water, it behooves you to convert that into a mass fraction before you try to do the process calculations. Okay, so now we have a solution that comes out of this, all right? And we cooled it down and the solution comes out, but remember, there's still solute in the solution. So our component balance would be F times the entry mole fraction is equal to S kilograms of solution times the solubility at that temperature plus C. And when I say solubility at that temperature, it's when it's already been converted into a mass fraction. Now, if you have a hydrated salt, that's what we're going to talk about here, then this stream also contains H2O that's actually in the solid. Okay, so what is a hydrated salt? A hydrated salt is a material that, depending on what temperature it solidifies at, it has a different amount of water attached to the molecule. So this is sodium thiosulfate dot 2H2O, or the dihydrate. And this one would be a pentahydrate. So it's good to learn those organic names for how many you have. Okay. So the salt that we have in the book that we can use is this. You're given information about magnesium sulfate, which is a hydrated salt. So you normally use magnesium sulfate as a hydrate because the anhydrous form, meaning the one that has no water attached to it, is highly hygroscopic, meaning that it readily absorbs water, which is a problem because then the properties of it change over time. So remember that now the actual crystal solid has 7 moles of water. This heptahydrate has 7 moles of water per mole of magnesium sulfate. So that's not an insignificant amount of water. So you have to account for that in your balance. So here's an example calculation. A saturated magnesium sulfate solution at 54.4 degrees, where its solubility is 35 weight percent, is fed to a crystallizer operating at 10 degrees C, where its solubility is 23 weight percent. So the first question is, which molecular product forms? So the crystallizer is operating at 10 degrees, so let's go back and see where's 10 degrees on here's 10 degrees. Okay, so 10 degrees is the heptahydrate. So we have 7 moles of water per mole of magnesium sulfate. And this simply comes from that fraction, okay? In that molecule, it's only 48.8 weight percent magnesium sulfate. You're looking at solid magnesium sulfate, but it's less even than 50% of that mass is actually magnesium sulfate. The 51.2% is water, okay, in the solid form. So let's do the calculation. Okay, from the given solubility at the inlet conditions, we see that we have 35 weight percent magnesium sulfate. The inlet feed rate is an unknown, and so the basis for the calculation is suggested to us that it'd be 100 kilograms per hour of crystalline product. Okay, so let's label our flowchart with all of our given information. Okay, we have solubilities here, solubility here given, and we have our basis for calculation, which is 1,000 kilograms of crystals per hour. So what do we have to feed and what comes out? So we have 2 unknowns and we can do 2 balances. So let's do our 2 balances. We have the overall balance, F is equal to S plus C. All right, and then we have a component balance, 0.35F is equal to 0.23S plus 1,000 times 0.488, which is the mass fraction of the actual magnesium. It's a component balance, so we're going to do a balance on the components. So there's 0.488 kilograms of magnesium sulfate in this thing here. Okay, so you can now calculate that we have F and S. These are our values. All right, you are ready for a video quiz. And here we go. A batch of 1,000 kilograms of KCl is dissolved in sufficient water to make a saturated solution at 363 Kelvin, where the solubility is 35 weight percent KCl in water. The solution is cooled to 293 K, at which temperature its solubility is 25.4 weight percent. So I have these 3 questions for you. What is the weight of water the KCl is originally dissolved in? Second is, what is the weight of solid crystals that form? Here, there's no hydration, so this is pretty straightforward. Here's a little tricky one. If 5 weight percent of the water evaporates during the cooling process, what is the final weight of crystals that form?